Hey everybody, welcome back. I want to do another video called Service Provider Architectures Part 3, and I want to focus on MPLS. So here we go. Where's my markers? Okay, I turned on my lights, so it should look better now. So we're going to cover multi-protocol label switching at a high level and a little bit of history and what it does for us as service providers, or even enterprises, should you decide to build out your network as an MPLS core. And I forgot to mention, we're also going to cover segment routing. So we're going to cover MPLS and segment routing in the service provider network. So in order to understand something, often you need to go back and think about where we were as an industry or as a society or whatever we're talking about. In this case, MPLS. Go back and see where the industry was and what was going on and what was pushing us to create this thing called MPLS. You know, necessity is the mother of invention. And so when things are necessary, people get smart, their brains start churning, and we start figuring things out. All right. So back in the late 90s, we had a lot of separate networks, and we had a lot of different disciplines that took care of those networks. We had time division multiplex telephony-based networks, where you had a group of telephone folks that were really smart about that and had been doing it for a long time. They knew all about how to do fractional T1s, DS3s. Then within that group, you had another group that was learning about SONET, synchronous optical network, and they knew how to configure virtual tributaries and OC, optical carrier connections, or STS, OC3 or STS3. And they knew how to plumb those TDM circuits into SONET nodes and carry them across the United States or across the world. So you had these statically configured, pretty rigid TDM or SONET-based networks that were handled by the telephone company, pretty much. And then you had some newer things going on with asynchronous transfer mode, ATM, which went nicely with SONET. And then you had another group of folks that were coming up learning about ATM and how to configure hierarchical PNI and scale out an ATM network. And then they had to learn LAN emulation on how to emulate Ethernet over ATM. And so in ATM, you could create private networks with PVCs or smart PVCs, you know, and so these two groups really didn't need to know about IP, Internet Protocol routing and things like that. Then you had your IP routing group that could do, you know, GRE tunnels or IPsec tunneling, and they knew all about routing, but they didn't necessarily have to deal with ATM, let the ATM guys handle that, and the ATM guys didn't need to know much about SONET or TDM because the telephone company could handle that. And so you had this opposite of convergence that was going on, where we had all these different types of networks to accomplish connectivity. And the customer could get private connectivity, but it was handled by these different groups. And so the industry was, I think, feeling the burden of what was going on, and I believe that was driving us towards converging the different types of connectivity into one. Now, where were we going to do that? Was ATM going to be the global technology? No, IP was. Internet Protocol was how the internet was ran, and that's where we were headed, was how to make the things that we needed to do take place over an IP network. That's where MPLS came in. MPLS transformed the service provider core from being an IP-only forwarding mechanism to being an MPLS-based forwarding mechanism, and we're going to get into that. So the service provider network, highlighted in red, it is the cloud. There's a lot of clouds. The cloud could be anything. But in this case, the cloud is the service provider network. Okay? When the service provider receives a packet or frame from a customer, that service provider node, in a traditional sense, will need to forward that typically based on an IP header. So the service provider ingress node will decapsulate it from its layer 2 framing structure, typically Ethernet, especially in today's day and age, Ethernet. And then it'll process it up to layer 3. It'll look at the IP header in that layer 3 protocol data unit, otherwise known as a packet, and it will look through its routing table and forward that based on the best IP route. That's the traditional sense of a service provider core. Now, I just described the traditional IP routed network. But to get that IP routed network to a place where it could provide private connectivity, virtual private connectivity, virtual private networks, VPNs, something had to happen. This is where MPLS came in. I'll say right away, not all vendor routers or operating systems support MPLS. So when MPLS became a standard, new router equipment or new upgrades to the router's operating system needed to take place in order for a router to support MPLS. Once that was done, you could then go and enable MPLS encapsulation on interfaces and enable a protocol that advertises those labels. All right? Now, the process between vendors, and I'm aware of Juniper and Cisco particularly, is a little different. Sometimes in one vendor, you enable a command and it actually is two birds with one stone type of thing. You turn on a command like MPLS IP on an interface, and not only does it enable the forwarding and encapsulation capability of MPLS, but it also enables the protocol that advertises those labels. Okay? Okay, I've been a little bit vague up to this point, but I'll get a little more specific. And I've been speaking about MPLS in two different regards for a reason. MPLS is a forwarding plane thing as much as it is a control plane thing. So think about it in terms of Internet Protocol, IP. An IP packet is an actual packetization mechanism whereby which we encapsulate user data on end hosts and encapsulate it for transport over an IP network. Well, how do those nodes know where to send that IP packet? Well, they know how to send that because of the control plane mechanism has learned the whereabouts of all those IP subnets in a network. So the IP packetization is the forwarding plane encapsulation, but the control plane is your IP routing protocols like ospf or BGP. Okay? And so MPLS has these same types of things going on. MPLS is as much an encapsulation, a shim header that causes traffic to be forwarded based on that shim header, as much as it is a control plane thing whereby which we need a protocol to advertise those labels so that the MPLS nodes know what to do with it when that PDU arrives. And I'll say this real quick, static routes. Static, I haven't even defined the term yet, but I'm going to use it anyway. LSPs, label switched paths. So those are created by human beings. And so when we're talking about static routes in an IP context or static LSPs, and we'll talk about that in a second, you're talking about a human being that has created those pathways in those nodes so that when the encapsulated protocol data unit arrives at that node, it then knows what to do with it. But in that case, the human being is the control plane. you don't want to be the control plane. As a person, you don't want to be the control plane. You want dynamics in your control plane. And for goodness sakes, in today's day and age with automation, you absolutely don't want to be, the human does not want to be or should not be central to the functioning of the network. Okay, so just wanted to put that out there. So more about the MPLS control plane and how these nodes in a service provider network learn what MPLS labels are going to be used for forwarding. First of all, when you enable MPLS on these nodes, they are now known as LSRs, label switching routers. The ones that have customer connections on them are known as LERs, label edge routers. So a LSR is a pure P node and a LER is a pure provider edge node. Okay? Now, how do they learn about MPLS labels? Well, that's where the control plane mechanism comes in. And one of the early versions, still to this day, one of the simplest ways to MPLS enable your network is using Label Distribution Protocol, LDP. Okay, so for the control plane, we have, for the MPLS control plane, we have LDP as one way to learn labels. All right? LDP, however, does not support traffic engineering. Now, another way to learn MPLS labels is using an old protocol known as Resource Reservation Protocol, RSVP. Years ago, RSVP was invented to provide bandwidth reservations and quality over an IP network. RSVP experienced a rebirth. Let me first say RSVP never really took off. However, RSVP had a rebirth when MPLS was invented, and RSVP was morphed a bit to support MPLS to be able to advertise labels as well as engineer traffic through your network. Became known as RSVP traffic engineering. I'm sorry, I'm writing that kind of low on the board. Sometimes known as MPLS-TE, multi-protocol label switching traffic engineering, is sometimes used interchangeably with RSVP-TE. Now, you can run LDP and RSVP-TE in your network. You can use RSVP-TE in some places where you want to engineer traffic and then let LDP do its thing otherwise. All right? So, now let me say a couple other things real quick. We've already talked about P's and PE's and C's and CE's. And so I'm sure you recall that the PE's from some of my earlier service provider architecture videos, the customer edge is that last router in the customer network leading into the provider. The provider edge is the router that has the connection to the customer. A provider node is one that doesn't have any customer connections. Now, when we're talking about this customer and how it might communicate with this customer over here, as the traffic flows from this PE to this P, across this PE to this P, and the swapping or label imposition and label disposition processes, pushing and popping and swapping, as those things take place, I want you to understand that this PE right here is a PE for the customer that it's connected to. Okay? What I mean by that, for this customer to talk to this customer site, as this traffic goes through this PE and through this P box, this box here, this node, is acting as a P box for that traffic that is flowing through the network this way. All right? I hope you understand that a PE box can also be a P box. But a P box cannot be a PE box unless it's configured as such. In other words, all MPLS nodes are able to forward information based on MPLS labels. Okay? However, a PE box has additional configuration. There's not configuration that tells a box to be a P box. There's not configuration that tells a box to be a PE box. What it is it's the VPN configuration. The provider edge has all of the VPN specific configuration that it needs to support VPNs. The PE has always been the heavy lifter in the MPLS topology. Okay? The PE is the heavy lifter. That's where the bulk of the configuration takes place for VPNs. The other nodes, the P nodes that don't have customers off of them, are purely swapping labels, and just a little bit of MPLS encapsulation and control plane to learn labels needs to be configured there. I'm going to put in the cards up here a lab that I did that shows step by step of building from factory defaulted Juniper, Junos, and Cisco IOS XR IP interfaces in an SP core, an IGP, the MPLS forwarding and control plane, multi-protocol BGP, the VPN v4 address family, the VRFs and routing instances, everything that's required to configure layer 3 VPNs step by step. I'm going to put that up there. You can watch that. But I just wanted to make that clear. Now, one more thing. These boxes that are now able to support MPLS can also still be IP routers. It's not that they can't route IP packets anymore. It's that they can do something additional to IP routing now. They can now additionally support MPLS. Okay? Now, back to control plane mechanisms for MPLS and how we learn labels. LDP takes every IP prefix in the routing table, assigns a label to it, and sends it to every LDP neighbor. We won't talk about how LDP neighbors are established. I do that in other videos. I'll try to leave links below and in the cards above on a little more about LDP. And I'm also going to do a video specifically on RSVP. I'm actually going to do an rsvp-te traffic engineering tunnel configuration video between Junos and Cisco IOS XR. So look for that in the future. Where was I? I remembered where I was now. So LDP looks at the entire routing table, assigns labels to every IP version 4 subnet, and then sends out that information. It's called a mapping, an address mapping. And the IP version 4 routes in your routing table mapped to labels is known as a forward equivalence class, a FEC. Okay, so LDP takes all those, creates forward equivalence classes for them, and sends them out to all the LDP neighbors. Okay, something different with that with rsvp-te is when you create an rsvp-te tunnel, it's between 2 points. It's between this point, for instance, and this point. And it would be for engineering the traffic in a certain way through your network. Okay? The thing I want to mention about rsvp-te MPLS label assignment is that the explicit path that the rsvp-te tunnel takes through the network is the only place that the MPLS label is put into the label forwarding table. Okay? So if an rsvp-te tunnel was established, I don't want to draw up the diagram too much, if an rsvp-te tunnel was established around this way, then these nodes would be the only places that the MPLS label for that rsvp-te tunnel, that's the only place those labels would exist. If you went here and you looked at the label, or you looked at the lib or the lfib, and I talk about lib and lfib in another video, those tables do not have those entries. All right, that's a difference between LDP and rsvp-te. And so this is where the industry has been for a couple decades. Label Distribution Protocol, or rsvp-te. This is how we would advertise MPLS labels to create what is known as a label switched path. The LSP is the totality of entries in the label forwarding information base that will allow a certain forward equivalence class to follow any given path or that specific path through the network. That's the LSP. So LDP and rsvp-te is where we have been as service providers for 15 or 20 years, okay? Now, what we always needed is an interior gateway protocol, IGP. The two types that service providers usually use are ospf and ISIS. That's always been there. You had to have an IGP to establish routing. You had to have an IGP to establish LDP neighbors between loopback addresses. You had to have the IGP in order to route that rsvp-te call setup message. The IGP has always been there. Now, in today's day and age, we have a new way of advertising MPLS labels. And the reason I was emphasizing that the IGP was always there is this. Segment routing is the new way of advertising MPLS labels. And in an MPLS network, SR is actually known as sr-mpls. And there's a reason I'm qualifying it like that, because there's other versions of SR, and we'll talk about that in a moment. Segment routing does not have its own label advertisement protocol, like LDP or RSVP. Segment routing's label advertisement protocol is the IGP itself. Isn't that great that the IGP has always been there, and now we're making use of it to advertise MPLS labels in a segment routing architecture. The way that we do that is with new link state advertisements or TLVs in either one of these IGPs, okay? But don't get too comfortable, because sr-mpls might not be here for very long. It'll probably be here for a while. But my point is, and I'll mention what I heard recently, is MPLS dead? Nah, I don't think it's dead. However, I say those two things to mention this. SR v6. Segment routing v6. So, segment routing is the control plane. However, segment routing, as I just taught you, does not have its own control plane protocol. Segment routing makes use of the IGP. It's always been there. Segment routing can have a couple different forwarding planes, MPLS or IPv6. SRv6 is segment routing over an IPv6 network. Look for my video on SRv6. It's pretty cool. You can do layer 3 VPNs, layer 2 VPNs over SRv6, which is over an IPv6 network. That's pretty cool, because we've always thought, well, a lot of us have thought, or that's just the way we've been doing it, is L2, L3 VPNs over an MPLS network. Matter of fact, we kind of set them in the same breath, and rightly so, because L2, L3 VPNs that are based on MPLS needed MPLS. However, those same concepts can be provided over SRv6. I'm going to do a video to show that. All right? Segment routing is also known as SPRING, S-P-R-I-N-G, Source Packet Routing in Networking. It's kind of interesting the way they made that acronym. The working groups at the Internet Engineering Task Force are known as the SPRING working groups. When you configure Juniper or Cisco for SR or SPRING, sometimes those acronyms show up in one vendor but don't show up in another. They're used interchangeably to speak of this SR technology. All right? Now, the information for forwarding packets or frames in a SR network is known as segment IDs, SIDs, SID, SID, a segment identifier. Now, SIDs that correspond to a link are known as adjacency SIDs. SIDs that correspond to the node itself is known as a prefix SID or a node SID. There's a few other types of SIDs. We're not going to get deep into SR. but I probably will later on in another video. But I just wanted to make that differentiation that in an SR network, you have this concept of a SID that's used for forwarding that information. Okay? Now, I bring that up because between sr-mpls and srv6, the SID is a completely different thing. Remember, in early versions of MPLS, and if you weren't around, I'll tell you real quick, there were two versions of MPLS, cell mode MPLS and frame mode MPLS. Cell mode MPLS was very specific to MPLS through an ATM network. The MPLS label or header was actually the ATM cell header, a virtual path identifier and a virtual circuit identifier. The VPI VCI value of an ATM header was absolutely repurposed to be the MPLS header in cell mode implementation of MPLS. Frame mode MPLS is what we know of MPLS today. It is the 32-bit shim header that we are very comfortable with today. Okay, that's why they called it a frame mode and cell mode MPLS, because you had the two versions back then. You don't hear frame mode MPLS today because it's really the only one that lived on, because ATM's dead. Now, I say all that to mention it's kind of reminiscent of that. The fact that segment routing's SID in an MPLS network is actually the MPLS shim header. That is the segment ID. It's the MPLS label value. The SID in an SRv6 network is the IPv6 header. And there's also an SRH, a segment routing header. If you learn more about V6, you'll learn that there's a lot of different types of headers in IPv6. There's one for SR known as a segment routing header. It doesn't always show up in every implementation of SRv6. Sometimes it's just the IPv6 header. Okay, so I wanted to make that distinction when dealing with SR. Okay, hey, I want to emphasize something. Everything that we've been talking about with the MPLS label or the segment routing SID and how those are advertised is regarding the core transport label. It is the label that is used to get that traffic from PE to PE across a service provider cloud. Okay, I'm emphasizing that because in VPNs, you at least have two labels. You have the label I just mentioned on how to get that traffic from edge to edge through that MPLS cloud. And then the other label that is also in use is what is known as the service label or the VPN label. So the mechanisms for label advertisements that we've been talking about is for that core transport label, for getting that traffic from edge to edge. Once that traffic gets to the other edge, the transport label is popped off. The label that is revealed is the bottom of stack label, and that is the VPN service label, which then helps that egress LSR to determine what VPN to put that traffic into and how to forward it to that customer. Okay, so we've been pretty much talking about the core transport label through this whole video, but you need to know that the VPN service label is advertised using a different mechanism. Multi-protocol BGP is how the service VPN label is usually advertised when BGP is in use. Okay, labeled LDP, otherwise known as targeted LDP, is another way that L2 VPNs, pseudowires, or LDP-based VPLS is another way that service VPN label can also be advertised. We did not cover the VPN label advertisement in this video. I do get into it in another one of my videos. I'll add it to the cards up here so that you can dig into that a little more. So that's that. Okay, so I hope that gave a good overview of some of the moving parts to the service provider networks of yesteryear and today and tomorrow. I really hope some of this that you're getting in this channel is helpful to you. If so, please subscribe. Share this with someone else that you think might benefit. Turn on those notifications so that you can get updates when I post new videos. And I look forward to the next time.